Good morning. First of all, I'd like to thank the organizers for inviting me to this Congress. And second, I must tell you that I'm very, very sorry for not being able to be there with you today. After about 40 hours in airports and airplanes, I had to come back home. And so this is the way that I will join you. And I will be connected when this is projected, so I will be more than happy to listen to all your comments or to get your questions. So today we will be discussing climate risk management in the agricultural sector, and basically we will be talking about two main subjects. One, very briefly, adaptation to climate change, and then most of the presentation on how can we improve the information for the agricultural sector. Adaptation to climate change. The first question that we get when we work in this area is, what do we need to adapt to? Or what can I expect of the future climate in my region? The best tools that we have available today to answer that question are the climate models, or GCMs. GCMs take the planet and they divide it into small grid cells, and then in each grid cell they take several layers up into the atmosphere and several layers down into the ocean and simulate the circulation of the atmosphere. Actually, these models are very similar to the ones that I used for weather forecasts, except that the climate scientists have changed these models a little bit so that they can add the effect of greenhouse gases in the atmosphere. Now, these are great tools and science has been advancing a lot, but there's still a lot of things that we don't understand. There's still a lot of problems with these models. For example, models don't even get the rainfall adequately in some regions of the world. In the past, they cannot simulate the past, for example, in Southeast South America. So they're great tools, but there's still a lot of limitations. The other big limitation of trying to use these models is that we need to tell the models how much greenhouse gas emissions will be throughout time. In other words, we need to imagine the world in the next 80 to 100 years. What technologies will be in use? What energy sources? How much of deforestation will be there? How many people will be living in the planet? And this creates a lot of uncertainty. So what the scientists did is create scenarios, socioeconomic scenarios. Some are more optimistic, some are more pessimistic, and then they connect those scenarios with emissions of greenhouse gases, and they run the climate models for different scenarios. The state of the art, the best knowledge that we have about future climate using climate models at the regional or local level, which is what farmers really need, is one, we know that temperature will very likely increase. We are not sure how much. We are not sure how variable that temperature will be. We know that it will probably be more variable than today. And we know very little about rainfall, future rainfall. We know very little at regional and at local level. That's the truth. We don't know what will happen with rainfall at the local level. And therefore, the scenarios of future climate with the best available tools are very uncertain. So we need a new approach. If we need to improve adaptation to climate change, we need a new approach. The approach that we are using consists basically of three things. One is to say climate change is a problem of today, it's a problem of the present, it's happening already, has been happening for a long time. As opposed to thinking of climate change as a problem of the future, of the year 2080 or 2100. No, climate change is a problem of today. Two, some of the most damaging impacts expected of climate change are those related to increased climate variability, to the frequency and the intensity of droughts, storms, floods, the same events that are damaging us, our production system today. And therefore, learning to adapt to today's climate to today's climate variability will lead to more resilient societies, including agricultural production systems in the future, with the advantage that the actions needed to improve the adaptation are needed today. We don't have to wait until 2050 or 2080 to see what the climate change scenario look like. It's today. What can we do today to improve adaptation to climate change? We can start by improving adaptation to current climate. So the rest of the presentation will be focused in that. What can we do today? One of the things we can do today is learn from the past. A lot can be learned understanding the past climate in our region. What are the main risks? What is a typical frequency of droughts? How intense are they? Floods? What is the problem with heat? Now, this analysis requires good data. I know that Australia has great data, but that's not the case in most countries in the world. So what we're doing is combining observations from weather stations with satellite estimated rainfall, for example. And we get maps like this, where we get information, daily data every 25 kilometers. Learning from the past also requires good analysis and interpretation of data. For example, good characterization of the climate-related risks. And then use that information to establish good insurance, accessible insurance policies. And we can discuss that later on if you like. Learning from the past also requires good analysis of what worked in the past. That is, what technologies worked well when we were confronting a drought? What soil or crop management practices were most successful? So this is when we do today, learning from the past. What about the future, the next season? What can we say about the next season, climate in the next season? This is where the seasonal climate forecasts come into play. And this is a typical map of a rainfall forecast. In this case, it's October, November, December of 2015. Now, what can happen with rainfall in the next 3 months? It can happen one of three things. Rainfall can be above normal, rainfall can be below normal, or rainfall can be around normal. If we know nothing of what will happen with rainfall in the next 3 months, these three classes have the same chance of occurrence, basically 33% each. And this is what is shown in the maps, in the seasonal forecast maps, as white areas. These are areas where basically we have no idea what will happen in the next 3 months. But then there are other areas in the maps with colors. Here in North South America and here in Southeast South America. In those regions, now you see that, for example, in Northern South America, the chance of getting rainfall below normal is 65, so twice as much as the historical. And the chances in Southeast South America of getting rainfall above normal is 80%. So this is what seasonal rainfall forecasts say. Basically, what is the probability that the rainfall in the next 3 months will be higher than normal, around normal, or less than normal? Now, when people understand that this is the information that you get from a seasonal forecast, their first reaction is huge disillusion. Basically, you are using supercomputers, using some of the brightest brains in the world, and this is what you produce. Now, I want to show you something that may change that perception. I'm going to use data that John Welsh provided me, and this is monthly rainfall from Moree in New South Wales. And what I did is I plotted the long-term mean monthly rainfall. So this is a long-term average rainfall for January, for February in millimeters per month. And you get during January, February about 70 millimeters, then lower rainfall in the cold months, in the fall and in the winter, and then again in the spring and beginning of summer, rainfall start again. Now this is a long term, this is the average year. What happens if I choose randomly 12 years, and I plot now the monthly rainfall of those 12 years in Moree? This is what happens. So still, the black line is the long-term mean, the average year, and then the other 12 color lines are monthly rainfall of each of those years. Try to find one year that behaves similar to the long term, to the average year. Don't even try. There's none. Basically, the probability of getting an average year is 0. However, think how many times we make some decisions based on this average year, based on a year that we know has probability equal to 0. So can we plan, can we decide based on probabilities that are greater than 0? That's the role of the seasonal climate forecast. So we are much better than before. Before, we only had information on average year or maybe some variability. So we're much, much better than before, but we can't expect more than what this seasonal forecast can give. A seasonal forecast will never be able to say you're going to get good rains. It's going to be a drought. What the seasonal forecast will tell you is changes in the probability of getting that type of year. Now, up to here, we have been talking about climate or climate-related information. If we want to inform decisions, inform agricultural policy, this is not enough. It's useful, but it's not enough. There's no decision that is made based on one dimension. Decisions take into consideration things like climate, prices, costs, characteristics of the farm, policies in place, personal preference, and many other factors. So we need to, if we want to inform decisions at the farm level, we need to integrate the information. Integrate climate information with agronomical information, economical information, information on markets. How do we do that? The approach that we use, we call it IDSS, Information and Decision Support Systems. We have been working in this for at least a couple of decades with very interesting results. Now, what are these information and decision support systems? They take climate information, they take data from remote sensing on the status of the vegetation or water or soil moisture. They take economical data. They use a lot of the data. Australia has a lot of data, very relevant data. Information about other dimensions, such as infrastructure. Then we use tools for analysis or simulation models. And then we integrate all that information using geographical information systems. And the results are maps like this, maps that are very simple. Behind these maps, you can have a lot of sophisticated science, a lot of sophisticated tools, but we find that if we want to inform, for example, a policymaker, the results have to be expressed in very easily understandable formats. And so using this approach, we have been working, for example, with regional governments or country governments, and help them to issue early warning systems to help in early response to emergencies, to establish crop production forecasts, disease or pest outlooks, help to establish good insurance policies, etc. Now, the nice thing of this approach is that you can work at different spatial resolutions. You can work at the whole country, or you can work at the province or state level, or you can go all the way into a farm. It's also nice that you can use it for different temporal resolutions. You can work in problems that are in the scale of days, or problems that are in the scale of seasons, all the way to decades or even longer term climate change. Now, in order for these systems to be relevant and to really inform decisions, they have to be easily understandable and they have to be actionable. They have to trigger action. It's not enough to be interesting. It's not enough to be good, relevant. They have to be actionable. It has to trigger some action in order to effectively inform decisions and plans. Now, at the farm level, what we have learned is that this approach of information and decision support systems are excellent tools for discussion support systems. What do we need? What do we mean by that? At the farm level, we have a lot of information, maybe climate, yield maps, irrigation data, soil data, prices, and we can use simulation models and then try to answer the questions of what if. For example, what would happen if I use this technology, if I use this crop, and if we have a El Nino or La Nina year? What happens if I change the technology, if I change the crop, if I change the irrigation method? What happens if I start crop rotations? What happens if the crop prices change? What happens if I introduce insurance? What happens if there is a new credit line? The nice thing of this type of tools is that it provides quantitative analysis to assess risks and inform decisions. This is a typical exercise an advisor, a consultant does with a farmer. What these tools add to that is the quantitative analysis. What is the probability, for example, if you use this type of technology, once every 3 or 4 years, you're going to end losing money. This is the type of information that the decision support system can provide. Now, we are already in the era of big data, right? It's amazing the amount of data that we generate. It's amazing the amount of data that we access. Examples at the farm level are yield maps, satellite images, information obtained with drones. And you get things like, in this case, these are 2 yield maps from an irrigated field and a rain-fed cotton field in Georgia. And of course, this is the typical yield maps show an amazing amount of variability within the fields, even in the irrigated fields. Now, if we don't understand what are the causes for that variability, these maps become just pretty pictures. We need to understand what is causing this variability. And number 2, once that we understand the causes, we need to understand if there are actions that we can take to reduce our variability. Is that related to fertilizer? Is that related to irrigation? As an example, the field in the upper left of the slide, it's an irrigated, I think it's a corn irrigated field. And irrigation in that field was based on soil-water balance, right? So when the soil water content reached 50% of the maximum available water, irrigation starts. Now, so it's good, it's rational, it's a good way to make decisions on irrigation. The question is, the irrigation is based on the soil-water balance of which soil? In that field, the soil-water holding capacity varied from 65 to 110 millimeters of plant available water in the same field. So how do we do to use that soil-water balance and irrigate in a way that we are not over-watering or under-irrigating? And then you have the interaction of climate with input, for example, nitrogen fertilizer. What happens if you have water excess? Likely have nitrogen as nitrate leaching, nitrogen losses as gases. So what is the role of this information and decision support approach? Is simulate a lot of combinations of this irrigation criteria, fertilizer criteria, considering the variability within the field, and optimize input use at the farm level. So what are these decision support tools doing? They're taking this amazing amount of data and they are simplifying that, resulting in something, again, that is actionable. I use a lot of information, I analyze a lot of information, I simulate a lot of information, but the result is something that is very easy to understand and triggers an action. So, 2 final comments. 1, on adaptation to climate change. I strongly believe that the most effective way to advance in adaptation to climate change is by investing efforts to improve adaptation to current climate. As I said, the scenarios for future climate produced with the best available tools are extremely uncertain. We know that temperature will increase, but we're not sure how much, and we're not sure how variable it will be. We don't know what will happen with precipitation at the local level, which is what we need to inform farming operations. And so, what can we do today? Let's start by improving adaptation to current climate. And that requires technologies, insurance, policies, a lot of combination of factors focusing in improving adaptation to current climate. And two, if what we want is to inform decisions at the farmer level or at the policy level, we need to translate and integrate climate information into lots of other types of information, agronomic, economic, markets, etc. For that, what we are using is this IDSS approach, this Information and Decision Support Systems approach. The result of that approach is, one, information that is easily understandable by farmers, by advisors, by consultants, and two, information that is actionable, that triggers action, that is a lot more than just interesting, it's actionable. It triggers an action. So I thank you very much for your attention, and once more, I'm extremely sorry for not being able to be there. I hope I'll be connected to get your comments and questions, and I strongly hope to be there in person very soon. Good day.